Hi guys, for this video lesson, we're going to discuss logical equivalence and conditional propositions under your General Mathematics from Quarter 2, Module 17. I'm your subject teacher, Arvin Enriquez. Our lesson objectives. At the end of this video lesson, you are expected to illustrate the different forms of conditional propositions. Verify the logical equivalences. State the converse, contrapositive, and inverse of a conditional proposition. And clarify a real-life instance using logical equivalence and conditional proposition. Let's go now with your logical equivalence and conditional propositions. Do you easily believe everything you hear? Definitely not. As a person, definitely not. So how do you know whether a thing is true or false? So we need some basis for us to conclude if that thing is a true or false statement. For example, it is difficult to claim the truthfulness of one thing without a basis because we really need to prove that our claim or the truth value of our claim is true, or if we really want to oppose that claim, then we need to prove that the truth value of that claim is a false, or that claim is a false statement. So we need some basis. So it is difficult for us to claim the truthfulness of one thing without a basis. So that applies, no, to everything. So the next time you receive hearsay, before believing, one thing you must consider is to let it undergo a process. So look for something, look some references or basis wherein that can help you, no, to prove that something that you hear or you receive from other people is a true, or even it is a false, no, at least you can counter check, no. That's why it must consider, no, that this one thing you must consider is to let it undergo a process. That's why there is a process, because sometimes there is no shortcut. Yes, it is, no, even in life there's no shortcut. Everything that we have is an hard earned, no, we need to deal with that hard earned beliefs that there is no shortcut in life. Let's deal now with your what's in. So in the past lessons, you have learned the different logical operators, including negation, conjunction, disjunction, conditional, and biconditional with their corresponding symbols. Now, these logical operators connect propositions. Yes, it is, no. If there are two or more simple propositions, then we use logical connectors, operators, or connectives, or that's what we call connectives. That will be your negation, conjunction, disjunction, conditional, and biconditional, to for us to combine, no, two or more simple propositions and to make them a compound ones. And truth values of said propositions can be determined using a truth table. Yes, it is, no. We can easily visualize if what will be the resulting truth value of that compound resulting compound proposition. So once we combine two or more simple propositions, then we apply your logical operators. What will be now the truth values of the resulting compound proposition? And by the use of that truth table, we can easily visualize and determine what will be the truth value of that resulting proposition. Now, let us see whether you can still recall the truth values of logical operators when used in compound propositions. So let's deal with this activity. For the first activity for this module, under your what's in, show me what is true. So your task now is to fill in the missing cells of the table. As you can see in the first column, there is a given truth values for your P proposition. And for your second column, that will be your truth values for your Q proposition. Now, whereas now to combine these two propositions, which are your P and your Q propositions, with this logical operator here, that will be your conditional. So P and Q. So if the first proposition is P and your second proposition is Q, so what will be the truth value of this one using your conditional? And the next thing is that when your Q becomes your first proposition here, and your second proposition is P, using the same logical operator which is your conditional, is it the same values that we can get from your third column? No? So you need to check if this P conditional Q is the same truth values that we can get from your Q conditional P. So it's up to you guys, no, to find out if they have the same truth values. Now for the last column, you're asked now to combine these two P conditional Q and Q conditional P with the concept of your logical operators disjunction. So meaning say right after we get the P conditional Q and Q conditional P, then we can now move forward in applying your disjunction between these two truth values, no, from your P conditional Q and your Q conditional P. So as you can see here for your P column, so we're now asked, no, to solve for the truth values of these if we combine, no, your third column and fourth column in this table. So what will be the resulting truth values? And that will be your truth values in your P column in this table. Now, as you can see in this here, there's a description that your third and fourth columns use conditional. Yes, it is, as you can see on the symbol being used, no, between your two propositions. All values for P conditional Q, that is P implies Q, are true except in the case where P is true and Q is false. As you can see, where is that? So that will be in this case, no, where your P is true and your Q is false. So except in the case where P, meaning to say that in this point, no, in your third column, that will be a false. The truth value in this case will be false in this case, as you can see. So on the other hand, all values for Q conditional P or Q implies P are true except in the case where Q is true and P is false. Where is that? Your Q is true and your P is false in the fourth row. As you can see that this is a false statement based on the description. No? The last column involves disjunction that P implies Q or Q implies P. As you have noticed, with the truth values you obtain in this column, all are true. And this will call a tautology. So again, your tautology is a proposition that is always true. That's how we define your tautology. So meaning to say, all truth values under your fifth column are true. And here, as you can see, there's only one false in your third column, wherein your P is true and your Q is false. It's the same thing with your fourth column, wherein your Q is true and your P is false. So the resulting value is that it is false when your Q conditional P. Once we apply your conditional here between your Q and your P. Now, that's how we deal with this activity. So it's up to you whether you go more about this one. So let's move on to our next activity. So for our Activity 2. Prove me I'm wrong. So we're asked to complete the table, as you can see below. So there's a P and Q proposition, and there are truth values under your P and Q proposition from your first column and your second column here. Now as with what will be the truth values for your P conditional Q or your P implies Q in your third column. So it's the same thing with your fourth column. So whatever your truth values from your third column, so we simply get the negation of this truth value. When we say negation, it's totally opposite of what will be the resulting truth values for your P conditional Q, and that will be your negation P conditional Q. In this case, for your fourth column. So right after getting the negation of P conditional Q in your fourth column, so we just simply apply your conjunction between your Q proposition and your negation P conditional Q for your P column here, as you can see. So again, no, as to recall above, in the third column P conditional Q, your P implies Q, all are true. All are true except in the case where P is true and Q is false. So meaning to say, this will fall here. That will serve that your P conditional Q or the truth value of your P conditional Q in this case will be false. Whereas the fourth column negation P, a conditional Q, negation of P implies Q, denies P conditional Q, thus making all that which are true in the third column as false, and with that which is the only false in the former as the only truth in the fourth column. So the fifth column involves the conjunction of Q, negation of P conditional Q, or Q and negation of P implies Q. So that's how we read it. Now, how did it differ from the last column? So in the first table. So if you have observed, this time all are false. So meaning to say, whatever your resulting values here, this will represent a contradiction, no? That will represent your contradiction or a fallacies. Policy, I mean. So this proposition that always result in false values is called a contradiction. So we simply use this symbol to represent that contradiction. So all these values under your pip column will be false. That's why this truth value or your pip column will represent now your contradiction or fallacy. Now let's deal with this what's new. So activity 3, so we're asked to complete me. So you're asked to complete the table. So decide for the truth values of the prepositions in the truth table below. So as you can see here, it's the same thing. There's a given truth values for your P proposition and your Q proposition in your second column. For your third column, what will be the P conditional Q or that P implies Q? So what will be the truth values for this column number 3? And for column number 4, what will be the negation of P? So simply the opposite of, the totally opposite of your proposition P under your first column in this table. Now, moving forward with your fifth column here, what will be the truth value of negation P, disjunction Q? So as you can see on this one, what will be your truth value for the fifth column? So there is an involvement of your fourth column here and your original proposition Q in the second column. So it's a combination of your second and your fourth column, applying the concept of your disjunction. Now moving forward with the last column or the sixth column, we're going to apply your third column, whatever your truth values in your third column, and the values that we can get from your fifth column. So it's a combination of your third column and your fifth column. So whatever the resulting values for this one, once we apply the biconditional between these truth values, no, from your column 3 and column 5. Now here, there's the guide questions for us to pond on. So we can answer these questions for us to easily understand, or for us to visualize more what this activity is all about. So for number 1, what truth values do you get for P implies Q, or your P conditional Q? Second, what truth values do you get for negation P? For number 3, what truth values do you get for negation P disjunction Q? And for number 4, what have you noticed with every pair of corresponding truth values in the third and fifth columns? And for the last question, what can you infer from the sixth column? So these questions will serve as your guided questions for you to understand, no, more what this activity is all about. So as mentioned in the other previous activity above, no, or from our previous activities, the conditional P and Q results to all true values except in the case where P is a true statement and your false is a false statement. So for negation P, values of P are simply negated. That is, P is true. Because if your P is a false statement, so if we are asked to get the negation of this P proposition, then it becomes true. Then your negation P is false and vice versa. So on the other hand, for the disjunction of negation P and Q are all true except when both negation P and Q are false. Yes, it is, no? Applying the concept of your disjunction. So comparing the third and fifth columns here, you can easily notice that they have the same truth values. Moreover, it turns out that when propositions perfectly alike, their biconditional will yield values that are all true. Yes, it is, no, dealing with your biconditional. Once your proposition are perfectly alike, if they are both true, true, or false, false, then it could be done with your biconditional. Hence, they result in a tautology, as observed in the last column. So again, your tautology here is a proposition that is always true. Let's move forward with our main agenda for this module. So let's deal with this. What is it? So two propositions P and Q are said to be logically equivalent if they have the same values in the truth table and if the biconditional P and Q is a tautology. It is not denoted by your by conditional Q or your P. As you can see, this symbol or symbols that we use to represent your biconditionals, then it's up to you. No, the above activity shows that your P conditional Q biconditional with the resulting value of this negation P, disjunction Q. So this logical equation is called Switchero law. So aside from this, below is a table of various logical equations. So let's move forward with the table of logical equivalence. So this table of logical equivalence, as you can see here, so let P, Q, and R be propositions. So first thing is that your identity law. When you say identity law, as you can see in this part, you'll see a tautology and a contradiction on this part. So your identity law compare them, no, to the equation. For example, if that is x multiplied by 1, so that will be equal to x. The value of x is unchanged after multiplying by 1. So we call the number 1 the multiplicative identity for logical operations. The identity for disjunction is f, and the identity for conjunction is true. So as you can see on this one, the identity for conjunction is true, and the identity for disjunction is false. As you can see, we're dealing now with your conjunction and your disjunction in this one. So that will be your identity law. So moving forward with your domination law, so compare them, we are asked to compare them to the equation. So we're using a more simple variables for us to understand what is a domination law. So for example, that will be x multiplied by 0. If we're going to multiply x by 0, then that will be equal to 0 for real numbers. So that's how we see your domination laws. The result is always 0. Once you multiply a number by 0, then that will be equal to 0 regardless of the value of x. No, regardless. The 0 for disjunction is true, and the 0 for conjunction is false. So once we apply this one, no, your conjunction, the 0 for disjunction is true, and the 0 for conjunction is F. So that's how we apply, or false. I mean, no, that's how we apply your domination law. Now, dealing with your idempotent law, there's a B, P, disjunction P, biconditional P. So it's the same scenario with this one. So we're just simply using your conjunction. So your P conjunction P biconditional P. So your idempotent law, no? For example, when an operation is applied to a pair of identical logical, for example, like this one, no? Once we apply, no? Apply to a pair of identical logical statements, the result is the same logical statements. So, for example, in this case, once we apply this pair of identical logical statements, still the result is the same logical statement. So, compare this to the equation. So, let's deal with this one. So, it's x squared is equal to x, where x is a real numbers. Yes, it is no. We assume that x is a real numbers. When your x squared is equal to x, it is true only when x is 0. Yes, it is no. Your x, if x is 0, because if 0 squared, so that will be equal to 0, and that will be equal to x, which is equal to 0, but or x is equal to 1. Now, this statement is a false statement when your x is 2, because 2 squared now is equal to 4. So if we substitute 2 to x, that will be equal to 2 only. That's why 4 is not equal to 2. But the logical equivalence P conjunction, no? Your P disjunction, your P, or here we use P, your P disjunction, your P biconditional P, and your P disjunction P biconditional P are true for all P. Yes, it is, no? That's why how we define your even what value of we're going to put as a value of your P here, no? As your P proposition, it will provide you uh, with a true statement, or is a true resulting value. That's why, but are true for all P. So meaning to say any value can be a value of this P, and it can provide you a resulting value which is true. Now let's move forward with your inverse law. As you can see here, your inverse law is your P disjunction negation P by conditional tautology. Then this will become your P disjunction negation P by conditional contradiction or fallacy. Now, this any statement is either true or false. No, this will serve as your inverse law. Any statement is either true or false. Hence, your P is the disjunction of your P is always true. Likewise, a statement cannot be both true and false at the same time. Hence, your P disjunction negation P is always false. So you need to take note of those things. Now again, any statement is either true or false. Hence, your P disjunction negation P is always true. So when you say that your P disjunction, as you can see, your P disjunction negation P is always true, then your P conjunction negation P is always false. So that's how we see the inverse law. That's why it is totally opposite of what I mentioned a while ago, no? Now, dealing with your double negation. So your double negation, as you can see in this one, so your double negation is that if we apply, the resulting value is still P. Why? Because if we apply your negation in your original proposition P, that is totally opposite of your original proposition. So right after, once we apply a double negation, then the resulting value is still your original proposition, because whatever your total whatever the opposite of that original proposition P, so if we take the negation of that P, so that will be your negation, totally opposite of the original. Then once we apply your negation again, then the resulting value is still the same with your original proposition P in your double negation. Now, with your associative law, now let's deal with this associative law. Now, roughly speaking, these properties also say that the order of operation does not matter. However, there is a key difference between them and the commutative properties. Yes, it is. No, there is a difference between these two, your associative law and your commutative law. As you can see in this one, your cumulative properties applies operation. No, let's talk about your associative and commutative law. Your cumulative properties apply to operation on two logical statements, but associative property involves three logical statements. So as you can see here, there are only two logical statements involved in your cumulative property or law, while on your associative law, there are three logical statements, your P, Q, and R. So stay still the same with the third column for associative law. So since conjunction and conjunction are binary operations, no? This conjunction and disjunction are binary operations. Now, dealing with your distributive law. Now, dealing with your distributive law, your P proposition, disjunction, your Q, whatever your resulting value with your Q conjunction R, by conditional your P, no? P, disjunction Q, conjunction P, disjunction R. So it's the same how we read with this one. So your distributive law, when we make two different operations on three logical statements, one of them has to work on pair of statements. Yes, it is, no? As you can see on this one, first forming an inner operation. That's why we put parentheses, no? We put parentheses because we always want to perform first the inner operation. This is followed by the outer operation to complete the compound statement. So we first we prioritize the inner operation. That's why we put parentheses right after dealing with your inner operation. Then this is followed by the outer operation to complete the compound statement. Now, your distributive law says that we can distribute the outer operation over the inner one. So let's deal now with your De Morgan, no? De Morgan's law. So when we negate, for example, when we negate a disjunction, as you can see, disjunction here. So once we negate a disjunction, respectively, a conjunction, so it can be disjunction or conjunction. So there's a conjunction here. So once we negate a disjunction or a conjunction, we have to negate the two logical statements. That will be your P and Q in these symbols. And change the operation from disjunction. So from this junction, as you can see, in this disjunction, that will be negation P, negation Q. So totally opposite of what is your original and your original P and Q propositions here. Now, and change the operations from disjunction to conjunction, respectively from conjunction to a disjunction. So that's how we deal with your De Morgan. So it can be changed from conjunction to disjunction or disjunction to conjunction. Now for your absorption law, here as you can see there's a P disjunction, whatever your resulting value, your P conjunction Q by conditional P, then your P conjunction P disjunction Q by conditional P. So your absorption law states that when your x plus xy is equal to x, for example, we use a simpler variable for us to represent this one, and the truth table for x plus xy is equal to s is proved that x plus xy is now equal to x your double I, and it can be on the proof that we can prove that your x plus y is equal to x. Now it's the same thing with this scenario dealing with your two logical statements with your P and Q propositions in your absorption law. Now with your switcheroo law, so there's a P conditional Q by conditional your negation disjunction Q. So the switcheroo law is the logical equivalence of your P, as I mentioned a while ago, that your P conditional Q negation P and Q, no, in the words expresses the equivalence. Now the equivalence between saying if P is true, as you can see, if P is true, then Q must be true. Saying either P is not true, or else Q must be true. So that's how we deal with your switcheroo law. So for example number 1, so using your logical equivalences, so verify that negation P conditional Q by conditional your P disjunction negation Q, and in your proposition, as you can see on your first column, so there's a given proposition and there's a given reason for the second column. So negation P conditional Q, that will be your given, and by conditional negation P, so we apply your double negation here. So disjunction Q, that will be your switcheroo law. And for the De Morgan's law, by conditional negation P, disjunction negation Q, and that will be your De Morgan's law here, and your biconditional P disjunction negation Q. That will be your double negation on this part. So moreover, the conditional propositions P P and Q can be illustrated in three other conditional statements. They are the following. First is your converse, contrapositive, and inverse. So conditional statements make appearances everywhere. No, we can say in mathematics or elsewhere, it doesn't take long to run into something of the form of if P then Q. So conditional statements are indeed important. We can say that. So what is also important are statements that are related, no, to the original conditional statements. By changing the position of your P, your Q, and the negation of the statement. So as you can see on this one, there is a change in the position of your Q and P and the negation of these propositions involved. So starting with an original statement, we end up with three new conditional statements that are named the converse, contrapositive, and the inverse. Now, so what's we see from this example is that no, a conditional statement has the same truth value as its contrapositive. So we say that these two statements are logically equivalent. We also see the conditional statement is not logically equivalent to its converse and inverse. Since a conditional statement and its contrapositive are logically equivalent, as you can see, no, we can use this to our advantage when we are proving mathematical theorems. So we simply use that concept with proving mathematical theorems rather than prove the truth of a conditional statement directly. No, we can instead use the indirect proof strategy of proving the truth of the statement's contrapositive. Now, dealing with your contrapositive here, contrapositive proofs work because if the contrapositive is true, due to the logical equivalence, the original conditional statement is also true. So please do take note of that. Again, your contrapositive proofs work because if the contrapositive is true, due to the logical equivalence, the original conditional statement is also true. It turns out that even though no, the converse and inverse are not logically equivalent to the original conditional statement, they are logically equivalent to one another. There is an easy explanation for this. So we start with the conditional statement if Q then P. So the contrapositive of this statement if P and not P then not Q. Since the inverse is the contrapositive of the converse. Yes, it is, no? The converse and the inverse are logically equivalent. So that's why in this example, no, there is a statement here that conditional and its contrapositive are logically equivalent. In the same manner, based on the given conditional proposition, its converse and inverse are logically equivalent also. And that will be your conclusion for this example number 1. So for example number 2, so given the following conditional, if you want lesser traffic, then pass through the ecotourism road. States its converse, contrapositive, and inverse. So your converse here, your Q conditional P. So if you pass the ecotourism, then you want to lesser traffic. So there's a use of if and then in this case. No? So there is a if and then in this case. So that will be your Q conditional P. Now, for the contrapositive, your negation Q and negation P, so we're just simply opposing what will be your converse in this side. So we need to put do not, does not, or it is not true. So if you do not pass through the ecotourism road, then you do not want lesser traffic. So that will be the contrapositive with what your converse Q by conditional P and bring to us. Now, what will be your inverse? Your inverse now is negation P, conditional negation Q. So if you do not want lesser traffic, then do not pass through the ecotourism road. So in your inverse, as you can see, so there is a switch, no? There is a change of position of your uh, proposition and logical operators that we use. So there is a negation, meaning to say totally opposite of what your original propositions. Then we change the location of your P and Q propositions. So for your activity number one, so tell whether the propositions your P conditional Q, disjunction negation Q here, and your negation P, disjunction Q are logically equivalent by filing in the correct logical equivalence for each statement. So in your first column, there's a given propositions and the reason why. So you need to come up with the idea that you can use your example na 1 for your reference, no, in dealing with this activity. And for activity na 1.2, it's the same thing on your example number 2. So there's a given propositions and you're asked to find the converse, contrapositive, and inverse. So you can put your answer in your Chatlayan notebooks and then you can pass this one on the said deadline. Thanks for watching. So please like, comment, and share, and subscribe.